We want to determine whether the following signal is an energy signal, a power signal, or neither. And to do that, we observe this signal, and you observe that it is a periodic signal because we know that any function that is a function of cosine or sine, then either of these two are periodic signals. And secondly, we generally know that any periodic signal is actually a power signal, but we cannot just state that and say that you have solved the problem. We ordinarily need to verify that indeed this function or this signal represented by this function is indeed a power signal. And how we do that is we know, so we have two rules that have scribbled down here. These two rules say that, these rules say that a signal is a power signal if the power of that signal is less than infinity and is bigger than zero. And its energy is approaching infinity. So these are the two conditions that we needed to show or to verify for this signal. So, so for us to do that, we needed first and foremost to evaluate the period of this signal. And how we do that is we know that the coefficient of time in this periodic signal is actually the angular frequency omega naught. And if we know the angular frequency of this signal, we can always evaluate the period by writing it in the form of below. We know that period is equals to the reciprocal of the frequency. And now if this frequency is expressed in terms of angular frequency, which is given to multiplying with 2 pi, all we need to do is to multiply at the numerator with 2 pi. That's why we have T is equals to 2 pi over omega naught, where omega naught is equals to 2 pi f. So once we know that that equation, and we have identified that our omega naught is equals to 44 over 21, then we can do very simple calculations, whereby we say 2 pi, 2 times 2 over 7, times the reciprocal of omega, which is 21 over 44. When you solve that, it gives you 3 seconds. And that is the period of the signal. So once we have evaluated that, we now need to evaluate the power or calculate the power of that signal and or the average power of this signal. And we know that the average power of a signal is of a periodic signal is actually given by this formula. So this is the formula that we need to plug in so that we can be able to evaluate the power of the signal. What this signal says is that the average power of a signal is given by the reciprocal of the period. Then you integrate the square of the signal of the period. So from 0 to t naught and the time with respect to dt. So once we do that, we know what our xt is, and we know our period. So we simply say 1 over 3. 3 is our period. Then you integrate cos squared of omega t plus theta. We know our omega is, we have just opted to work with omega instead of this value because we can get lost along the way. And the signal here, the amplitude of this signal 2, we just put it outside the bracket or the integral so that we have 2 squared. So we are squaring everything of our signal. So we have cos squared omega t plus theta dt with respect to, sorry, this is 3, from 0 to 3. So once we have done that, we can use this trigonometric identity that says cos squared of A is equals to 1 over 2 to bracket 1 plus cos 2a. And therefore, because we can now set this omega t plus theta to be equivalent to 2a, then we can simply evaluate and we find that cos omega squared omega t plus theta will be equals to half to bracket 1 plus cos 2 omega t plus 2 theta. Therefore, moving forward, we can now evaluate our integral. Remember, we put 2 squared outside and over 3. I just separated them. And now if you recall that we have introduced a half of function of this, then we can actually find out that the amplitude is coming out to be equivalent to 2 over 3 because this cancels with this. You're left with the 2 over 3, and that is where we have there. Then when you integrate 1 with respect to t, it simply becomes t, and the limits of integration are calculated them as such. And when you integrate this, it is going to give you a sine 1 over 2 omega, and then the function remains right there. So, and then of course the limits of integration are going to remain as such, and we can still close our bracket. So when you do that and you perform this, you're going to find that it's going to be 2 over 3 times 3 becomes 2. And then when we evaluate this function is very small figure which is actually less than 2. So we can, even without going into solving this into completion, we can actually find that our average power signal is actually less than infinity. And once we have done that, we can actually agree that our signal is a power signal and not energy signal.